Have you ever just stopped and wondered how the universe got its rules? Well, we're about to go on a journey. A trip back to the very first second of time itself to see how the four fundamental forces that literally shape our reality came to be.
You know, everything from the way your phone charges to the reason the sun shines in the sky, it all boils down to these forces. But here's the big question, the one that keeps physicists up at night. Were they always four separate things? And the answer, as it turns out, is a definite no.
All right, so let's meet the main players in our story today. You've got the strong nuclear force, which is like the universe's superglue, holding the core of atoms together. Then there's the electromagnetic force, giving us everything from light to lightning. You've got the weak nuclear force, the one behind radioactive decay. And of course, good old gravity, keeping our feet on the ground. Four forces, all with completely different jobs and strengths. So here's our game plan. We're diving headfirst into the universe's very first second, exploring these incredibly brief yet absolutely world-changing eras. Each one represents a huge shift, a moment where the very rule book of physics was being written and then rewritten. Okay, first stop, the Planck Era. We're talking about a time so early, so unbelievably extreme, that our modern laws of physics just completely fall apart. This is the realm of pure theory, a place of unimaginable heat and energy.
Get ready for this number. 10 to the 32 Kelvin. That's a 1 followed by 32 zeros. I mean, you can't even really wrap your head around that. At this insane temperature, the universe was so hot, so dense that there was no difference between any of the forces. They were all just one. A single, perfect, unified superforce.
But you know, that perfect unity just couldn't last. As the universe began to expand, it started to cool. And this cooling is key. Think about steam condensing into water, and then that water freezing into ice. As the universe cooled, the forces did something just like that. They froze out from each other, one by one.
And boom, the very first split. The first tiny crack in that perfect unity. At an impossibly small fraction of a second after the Big Bang, gravity just pieced out. It went its own way, leaving the other three behind as a still unified force that physicists call the gut force for grand unified theory. Now this whole process has a really cool name, symmetry breaking. And it's not just some random event, it is the fundamental engine that drove this entire cosmic separation. It's how we got from one force to four. So what does that actually mean? Well, picture a perfectly round, still puddle of water. It looks the same from every angle, right? It's perfectly symmetrical. But then the temperature drops and it freezes. All of a sudden you have these intricate, complex ice crystals pointing in specific directions. The original symmetry is gone, it's broken. That is exactly what happened in the early universe, but with forces.
Okay, on to the next split. Around 10 to the minus 36 seconds, the universe cooled a bit more, and it was the gut force's turn to break. The strong nuclear force peeled off on its own, leaving electromagnetism and the weak force still teamed up in what's called the electroweak force. And let me tell you, this was not a quiet breakup. The energy released when the strong force split off was absolutely colossal. So huge, in fact, that many scientists think this is what kicked off cosmic inflation. That insane period where the universe expanded way faster than the speed of light.
And now for the final separation. As the universe kept cooling, a brand new player entered the game, the Higgs field. As it settled into place, it did something very specific. It latched onto the particles that carry the weak force, the W and Z bosons, and gave them mass. But it totally ignored the particle for electromagnetism, the photon, leaving it massless. And just like that, because one got heavy and one stayed light, the electroweak team was no more. And there we have it, four distinct forces.
So, the forces are all separated. The cosmic rulebook is written. Now what? Well, now it's time to actually start building things. The stage is set for matter to make its grand entrance.
For a tiny fraction of a second, the whole universe was this wild, hot soup called a quark gluon plasma. You had the fundamental building blocks of matter, quarks, and the particles that carry the strong force, gluons, all just zipping around freely. It was a primordial soup made of the most basic stuff imaginable.
But, as always, as the universe cooled, the party had to end. The strong force finally got strong enough to do what it does best: confinement. It started grabbing those free-roaming quarks and glued them together into bigger particles called hadrons. The most famous of these, and the most important for us, are the baryons. You probably know them as protons and neutrons, the very core of every single atom in existence. Okay, so we've built our first particles, but there's a problem. The universe is still a super dense, hot fog. Light is trapped, it can't go anywhere. What happens next is honestly one of the most dramatic, cinematic moments in the history of the cosmos.
Imagine this. For 380,000 years, the entire universe was like being on the inside of the sun. It was a scorching, thick plasma. Anytime a photon, a particle of light, tried to move, it would immediately slam into a free electron and get scattered. You literally couldn't see through it. The cosmos was completely opaque.
But then we hit a magic number, 3,000 Kelvin. Yeah, still incredibly hot, about the temperature of a red star's surface, but this was the tipping point the universe had been waiting for.
At this temperature, those freewheeling electrons were finally moving slow enough to be captured by protons, forming the first stable neutral hydrogen atoms. And with all the electrons now locked into atoms, the path for light was suddenly clear. In a single moment, the universe went from an opaque fog to perfectly transparent. All that trapped light was set free, and the cosmos lit up for the first time. We can still see the afterglow of that first light today as the cosmic microwave background.
And that incredible event brings us, more or less, to the modern universe. All of that cooling, splitting, and building resulted in this, our current understanding of how everything works, an elegant and powerful theory called the Standard Model of particle physics. It's a masterpiece, with one very famous exception.
So this is the universe we live in now. 4 distinct forces, each with its own personality. You've got the unbelievably powerful but very short-ranged strong force. You've got the long-distance players, electromagnetism and gravity, with wildly different strengths. And you have the weak force, doing its own crucial work on a tiny scale. This is the cosmic landscape today.
And this is the rulebook. The Standard Model is basically the universe's parts list. You have fermions, which are all the matter particles. You have the gauge bosons, the force-carrying particles we've been talking about. And then there's the one-of-a-kind Higgs boson, which gives other particles mass. It's the whole shebang. Well, almost.
And that almost is a really big deal. The Standard Model is a triumph of science. But notice what's missing? Gravity. Remember how our story began with all 4 forces united as one? Our best theory today can only explain 3 of them together. Bringing gravity back into the fold, finding that theory of everything, well, that's the holy grail of modern physics. It's the grand quest to finally complete the story that began in that first fiery instant of time. What do you think is out there waiting to be found?